Hi, so welcome to the fifth lecture, and today we are going to discuss normal distribution, z-statistics, t-statistics, and confidence intervals computing. But before we proceed to those issues, perhaps it would be useful to start with the idea of probability distribution and normal distribution in general. So, we are going to concentrate on continuous numerical variables only. And for continuous random variables, probability distribution can be represented by a smooth curve, a function of x which will be denoted as f of x. This curve is called density function or frequency function. And when we use this distribution, the probability that random variable x falls between two values, let's say a and b, is area under the curve between a and b. On this graph, you can find an example of normal distribution. Normal distribution can be computed based on the value of mean of the random normal variable. In this case, we discuss population mean, mu, and standard deviation. So you already know how to compute those values for a set of data, and here you can find the formula. Luckily for you, we're not going to use it that much. However, we are going to use the idea of normal distribution a lot. So, any continuous numerical random variable will produce similar bell-shaped distribution. This is like the fundamental property of the data. If this does not seem intuitive for you, let's discuss some distribution based on some particular example. So imagine that we treat grade point average of Polish students as normally distributed random variable. It's continuous and it's numerical, that's why all the conditions are fulfilled. Imagine that the average grade for all the students is, let's say, 3.5. So here we have it. And the idea is that if you pick one person randomly from the population of Polish students, the probability that this person will have GPA equal to 3.5, which is population mean, will be the highest. If you seek for smarter students, students with higher GPA, so the value of the variable increases, the probability of picking the student randomly from the population of Polish students will decrease. The same will happen if you assess students with lower grade point average. Again, the probability will decrease. So yeah, as I mentioned before, we know that any continuous numerical variable is likely to be normally distributed. Again, this is like a fundamental property of the data. And standard normal distribution is a normal distribution with mean equal to 0 and sigma equal to 1. A random variable with a standard normal distribution will be denoted by symbol z and will be called a standard normal random variable. So the idea is that you can take any variable, normalize it, and obtain this value. So this is the representation of standard normal distribution. Because of the assumptions we introduced, the formula is less complicated, but again, we're not going to use it. So here, the mean value is equal to 0, and the value of standard deviation is equal to 1. So as I mentioned before, we typically use standard normal distribution in order to detect probability that certain value falls within certain range. For instance, let's consider the following example. We have to find the probability that the standard normal variable z takes the value between negative 1.21 and positive 1.21. So here you have to keep in mind some fundamental properties of normal distribution and standard normal distribution. The area below this curve is always equal to 1. And I believe it makes perfect sense, because if you compute all the probabilities, you shall always obtain 1. And of course, probability cannot be bigger than 1. So for instance, if you consider all the possible outcomes and you aggregate the probabilities associated with those outcomes, you should always get 1. So I believe this is pretty intuitive. In addition, this distribution is perfectly symmetrical. So this area is equal to this area, and they are both equal to 0.5. So here we have to find the probability that standard normal variable z takes the value between negative 1.21 and positive 1.21. So first of all, it would be useful to depict standard normal distribution and denote the area we are going to investigate. So here we're interested in probability that z falls within this range. And of course, if you are good in math and you are familiar with the idea of integral, you might compute this area. But it will be extremely time consuming. That's why we can use the table. In your textbook, it's provided in Appendix D. So this is the extraction from this table. So we are interested in 1.21. So here I pick 1.2, here 0.01, and the resulting value is 0.3869. So this is how we interpret it. The area between 0 and this value, I mean this one, will be equal to 0.3869. Also, we know that this distribution is perfectly symmetrical. So when it comes to this area, it should be equal to this one, because we have pretty identical values here. So again, we know that area between 0 and 1.21 is equal to 0.3869. And we know the distribution is symmetric, so the area between negative 1.21 and 0 will take the same value. So the entire area is equal to 0.7738. So we can conclude that probability that standard normal variable z takes the value between negative 1.21 and 1.21 is approximately equal to 77%. Let's consider another example. Let us try to find the probability that the standard normal variable z is bigger than 1.44. Again, it would be extremely useful to use this graph. And from the table, we can find the value of this area, this probability. But we know that the entire right-hand side part of distribution is equal to 0.5. So first of all, we go to the table. 1.4 and 0.04 give us 1.44, and this is the corresponding value. So we know this value. We know that the entire part, right-hand side part, is equal to 0.5. That's why we can subtract 0.4251 from 0.5, and as a result we get something close to 7%. So we can conclude that probability that is bigger than 1.44 is approximately equal to 7%. There is another rule using which we can convert a normal distribution to a standard normal distribution. So if x is a normal random variable with mean mu and standard deviation sigma, then the random variable z will be defined by the following formula and have a standard normal distribution. So for instance, we can use this knowledge in order to solve the following problem. Assume that GPA of Polish students is a normally distributed variable with the mean value of 3.7 and standard deviation of 0.8. We have to find the probability that the randomly picked student will have a GPA between 3 and 4. So first of all, we have to find the probability that x takes the value between 3 and 4. We can use this formula in order to compute the variable z. So here we take this value, subtract mean, divide by standard deviation, and the same we have to do with the upper value. After very simple calculations, we know that we have to find probability that falls between negative 0.88 and positive 0.38. So this is the area we are interested in. Now we have to go back to the table and we have to find the respective values. So we are looking for 0.38 and 0.88. And as the result, since we know the distribution is symmetrical, we have to sum them up, and this is the probability we get. So we can conclude that probability that randomly picked student will have GPA between 3 and 4 is approximately equal to 46%. Okay, so actually that was it when it comes to the first part of the lecture. Hope it was clear, and see you in the next video.